Okay, chapter 1 is the basics of geometry, 1.1, points, lines, and planes. I'm going to start out by talking about the Pythagorean theorem. The book doesn't actually talk about the Pythagorean theorem till much later, until a later chapter, but it always annoys me a little bit because there are problems where you could use the Pythagorean theorem and it's very useful. And I think a lot of you have probably seen it before, so I'm just going to introduce it, even though it's not going to be tested directly in this chapter. It's just useful, okay? So the Pythagorean theorem is only for right triangles. It has to be a right triangle. So for any right triangle ABC, so ABC would be the vertices, the three corners of the triangle, then we can say, so if I draw a picture of ABC up here, has to be a right triangle. Okay, so there's my triangle, and if side A is going to be across from angle A, and usually we'll use lowercase for the sides, so that you can see side A is across from angle A, side B is across from angle B, and this is supposed to be a lowercase c over there. For any triangle like this, a squared plus b squared is going to equal c squared, okay? A and B are the legs, as opposed to C, which is the hypotenuse, okay? So maybe you remember what the hypotenuse is. If you don't, the hypotenuse is always the longest of the three sides, and it's always across from the right angle. So in this particular picture, this would be the hypotenuse. So longest, and it's across from the right angle. So it's really important. This is my little symbol for angle that I'll use a lot, just so I don't have to write out the word angle, okay? So it's across from the right angle. It's really important that you are able to identify the hypotenuse in order to use the Pythagorean theorem correctly, okay? So in this picture, my hypotenuse, just putting HYP for hypotenuse, it's right there. I know it's right there because it's across from the right angle. Also, it looks like the longest side. Sometimes it's hard to tell by looks what side is the longest, but you can always tell based on where the right angle is, okay? So that means when I'm setting this up using this formula, my A and B, the legs, are going to be x and 5. Now, it doesn't really matter which one's A and which one's B, because x squared plus 5 squared is the same as 5 squared plus x squared. It doesn't really matter. The commutative property of addition allows me to switch the order of those. So it doesn't matter if I say x squared plus 5 squared or 5 squared plus x squared. Okay? But it really does matter that the 13 squared is the one that's on its own. That's where the hypotenuse goes. Okay, so that's the C. Okay, and then I'm going to start to simplify this. So 5 squared is 25. 13 squared is 169. Okay, and then I'd want to subtract 25 from both sides. My goal here is to get the x by itself. So first I need to get the x squared by itself. Okay, so I'm going to subtract 25 from both sides of the equation. Now x squared is going to equal 144. And now I'll take the square root of both sides of this. Okay, and you could put it into a calculator. You probably know the square root of 144 is 12. Now you might say, wait a second, isn't negative 12 times negative 12 also positive 144? And it is, that's true. But I couldn't have the side of a triangle be a negative number because it's a distance. You can't live negative 12 miles away from school, right? It's no matter what direction it is, it's always going to be positive, okay? So now I've solved this for x. And when I'm doing examples, I usually like to put a box around my final answer, especially if it's a numeric answer. I mean, if it's a whole sentence or a paragraph or something, or even a diagram, that might not make sense. But in general, it's nice to put a box around the answer. That way, if I'm grading your test or quiz, it's easy for me to tell what your final answer is. Otherwise, it can be difficult sometimes. Okay, so now I'm going to get to the stuff that's really in this first section, and most of it's just some basic vocab. So a lot of which you're going to know already, okay? So let me just separate this a little bit. A point, well, a point is a location, okay? So I put a little dot here. I'm going to put an A above this. This would be point A. It's a location. It's a place. There it is, right there, right? Yeah, and you just call that point A, all right? And then a line is indicated by 2 points. So if you pick any 2 points in the universe, so let's say points A and B, there's only going to be one straight line that goes through both of those points, okay? So we can say that a line is determined by 2 points, okay? And naming this, we can call this, you could write out the word line. This could be line AB. You could also use this symbol, okay? And this would be the same as, it doesn't have to be alphabetical for lines. It doesn't matter. So BA, line BA is the same as line AB. They're the same thing. Okay, it's just the line that goes through both of those points, whatever order you say the points in. Okay, and then we've got a line segment, and a line segment is part of a line. Okay, so a line, these arrows indicate that this goes off on forever in both directions. But with my line segment, there's endpoints. So if I call this A and B again, that's the end of the road on both sections. So it's just a part of a line, okay? And you can write out line segment AB or BA, but usually we're going to use a symbol like this, and the order doesn't matter again. It's just the line segment that connects those 2 points, okay? And then array is a combination of these two things. So it's half line segment, half line. So array is going to, it has one endpoint, even though I kind of think about this as the start of my array, but it's called an endpoint because that's the end of the road if we're going that direction, okay? So if I call this point A, this is the endpoint. And then I'll put B over here. It's going to go past B and through B and go on forever in that direction, okay? So when I'm naming this, the order does matter. So we can use a symbol. You can write out ray AB if you want, but you can also just use that arrow above. That's just one-sided, okay? And you have to start, it's maybe a little counterintuitive, but you start with the endpoint, okay? So this is not the same as ray BA. So I'm going to cross that out. I want to indicate not the same thing, okay? BA would actually go like that, right? Because it would start with B, the endpoint's B, and it would pass A. So BA would be heading in the opposite direction and starting from, well, have an endpoint of B, okay? Which brings us to opposite rays. So these two rays that I drew here, some people might assume that those are opposite rays because they're going in opposite directions. But that's not actually what an opposite ray are. Those aren't opposite rays. An opposite ray is going to have the same endpoint, opposite directions. Okay, so in other words, they can't be overlapping like those two that I drew up there. In my picture here, I've got a little gap. So I'm just going to put a point there. I'll call this, well, I'm going to put 3 points on here. I'll label those A, B, and C. So I'm just going to color code this a little bit. Don't worry if you don't have colors, but just so you can tell what I'm talking about. So I've got a ray that starts at point B that goes to the left right there. And then I've got another ray with the same endpoint but going to the right. Those two, the orange and blue ones there, would be opposite rays. Okay, so so I could say this orange one I'd call ray BA because it starts. This is the end point, and then it goes. So here's where it starts. It goes past A. So I could say BA, and the blue one would be BC. Ray BC are opposite rays. Okay. All right, and then I didn't plan this out very well with my spacing, but I've got one more piece of vocab at the very bottom of the piece of paper here. Collinear points. Collinear. So that just means they're on the same line. Okay? Points on the same line. Okay, so in this picture above, points A, B, and C would all be collinear. So if they're all lined up, they're going to be collinear. These two are collinear. Those two are collinear. Actually, any 2 points are going to be collinear because you can always draw a straight line through 2 points. But if you have a third point, they might be kind of arranged in a triangle, and then you couldn't draw a straight line through all 3. Okay, so collinear points are going to be lined up. Okay. All right, on to the next page here. Okay, my phone went off, so I had to make an edit there. Okay, here's the second page. A plane is a flat surface that extends infinitely in all directions. Okay, so if you look at this diagram right here, this parallelogram piece is supposed to represent a plane. Okay, now but you have to imagine that it goes on forever. Like this piece of paper could represent a plane that I'm writing on, but it doesn't end at the edges. It just goes on forever. You can't really draw that, but that's what a plane is. So you just kind of take a piece of it to draw it. Usually it looks like a parallelogram in diagrams. Okay. It's determined by 3 non-collinear points. Okay, so if you take any 3 non-collinear points, that just means you don't want them in a straight line. So really, if they form a triangle, they're going to be non-collinear. Then there's only going to be one plane that would go through those 3 points. So, you know, if you color in the triangle and just extend the triangle, it will form a plane. So 3 non-collinear points determines a plane. Okay, so let's look at this diagram. All right, let's name the plane in 3 different ways. So since it's determined by 3 non-collinear points, an easy way to name a plane is just to pick 3 non-collinear points that are on it. Okay. Now I wouldn't want to pick these 3 points. These S, P, and T are all on that plane, and this is a little bit hard to show you here. I'll try to use my phone here. So if this is a plane where all 3 of those points S, P, and T are on it, I could kind of swivel this plane like that and have a different plane with those same 3 points. So that's why it doesn't work if they're linear. Okay. But if I choose, let's say I choose these 3 points, S, P, and V, those are all on that plane. And so if I extended that triangle, I'd get that plane. So I could call this plane SVP. Okay, it doesn't really matter what order those 3 letters are in. So you could just jumble those around and get some different ways to name this. But I'm going to, just to make it more interesting, I'm going to use some different points for my other names. So I could also call this, let's say I could use these 3 are all on that plane and they're all non-collinear, so I could call this plane SVT. And again, I could just jumble the letters to get different names. Okay. Now, most of the points on here, the letters on here are right next to points. R is not. Okay. So, you know, they could have put a dot right there at the corner if they're trying to indicate that this is point R. But since it's not attached to a dot, what they're trying to tell us is that you could also just call this plane R. Okay. So that's another way to name a plane is if there's a letter that's somewhere floating on it that's not attached to a point. Okay. Now you might notice that N and M are also don't appear to be attached to points, but those are lowercase, and that means something different, and I'll get to that in just a second, okay? But before I do that, name a point that is not on the plane. Well, point F is kind of interesting. It's hard to tell because if I extended this plane, I don't really know if F would be on it or above it or below it. So what I want to do for this part B is choose a different point. So the best answer for part B would be point Q. Okay, and point Q, I can tell that's not on the plane because you see how this has a dashed line. That means that this line is piercing through that plane. So this little part is underneath the plane. And so that goes through it. So I can see it goes through it at point P. So point Q must be above the plane. So point Q is definitely not on that plane. Okay? Point F, you could make an argument, but it's hard to tell. Is point F on the plane? I don't really know. Technically, I'm going to say not enough info. Okay, I can tell you that the book, if they draw a point that's not on it within the parallelogram, they probably mean that that's not supposed to be on the plane, but I don't know for sure. It might be if I extended this plane. Okay. All right, and then our N and M points or lines. Well, N and M are the only two letters on there that are lowercase. So usually lowercase is used for lines. So these are going to be lines. Okay, so I can call this line ST or SP or PT, but since it has that lowercase name, I can also just call that line M and line N. And I can tell because they're lowercase. So I'm saying lowercase is for lines. Okay. All right. Collinear points are on the same line. Coplanar points are points that lie on the same plane. Okay. So let's look at this next example here. I've got a picture of a box. It looks like a cube. Okay. And I'm going to name 4 coplanar points. So I want to look for 4 points that are on the same plane. Okay, so in this book, they're usually talking about the sides of the box as the different planes. So there would be 6 sides to this box, right? The top and the bottom, the left and the right, the front and the back. So there would be 6 sides. So I just need to find 4 points that are all on the same side. So these ones work out pretty nicely because they're all on the back of this box, right? So I'm going to say A, B, C, and E. Okay, if I throw point D in the mix, then it's going to be hard to find a combo where they're going to be coplanar. Okay, so I'm going to end up with non-coplanar points, and it's a little hard to visualize. But let's say I chose, I don't know, let's say I'm choosing this point and this one. I use those 4. Okay, now you'd have to kind of bend down the plane. It'd have to curve or turn a corner in order for it to draw a plane that goes through all 4 of those points. And planes are flat. They're not curved and they don't turn corners. So those 4 points are going to be non-coplanar. Okay, now this is not the only set of 4 points that are non-coplanar here. Really, you could choose any combination with point D in the mix. Okay, there is one example. Now, I don't have a name for this corner right here, okay? But let's say I chose these 4 corners. Your book is going to say that those are non-coplanar. But I would argue that they are planar because there is a plane that goes through all 4 of those. So if you kind of imagine slicing this box on a diagonal like that, there is a plane. It's just not one of the planes that's already drawn, but there is a flat plane that goes through those 4. Okay, that's kind of a technicality, but I would say those are coplanar. Your book says they're not because it's not one of the 6 planes drawn, but there is a plane. Okay, all right, and then the last 2 examples here, we've got intersecting lines here. So when lines intersect, and they don't have to intersect, they could be parallel or they could be skew lines, which we'll get to later. But when lines do intersect, like in this picture, they're going to intersect at a single point. Right, so there's my intersection. Intersection is just the points that are shared by both lines. Okay, so you can also have intersecting planes. So I'm thinking about these two planes, what points do they both share? Well, this point would be on both planes, right? So would this one. So would this one, and this one, and this one. So actually all of the points on that crease would be on both planes, right? So some people are going to look at this and say, oh, intersecting planes are going to intersect at a single line segment. But you got to remember that these planes go on infinitely, left and right, up, down, in all directions, okay? I can't really draw that, but this plane goes on that way. So that means that this crease would also continue infinitely in both directions. So these are going to intersect at a single line, not a line segment, okay? By the way, you can have parallel planes as well, planes that don't intersect at all. But when they do intersect, they're always going to intersect at a line. Okay, and that's it for the first section.